Hi, good morning. My name is Ahmad Izzuddin bin Muhammad Amin, and my groupmate is Syed Muhammad Alif bin Beke. So in this part, I will be presenting about the buck converter for assignment in industrial power electronic. So moving on to the next slide is we were assigned to design a feedback controller for switch mode power supply. So we were given the feedback controller of a buck converter that consists of PI controller, PWM, switch, and filter and load. So the thing is, we were assigned it to explain the operation and find the transfer function. So basically, the buck converter is a fundamental component in power electronics. It integrates a multi-stage process to regulate voltage output efficiently. And then we initiate by an input voltage from a power source, and it navigates through various stages ensuring precise voltage delivery until the load. The proportional integral PI controller, a very important element, is it differentiates between the desired and actual output voltage. This compression generates an error signal, very important for subsequent adjustment. It also employs this error signal, and the pulse width modulation (PWM) circuitry shapes the on and off pattern of the switch. It's similar to like a MOSFET or BJT. The switching mechanism controls the energy flow, modulating the input voltage in tandem with the PWM signal characteristic. Following this modulation, uh, the signal travel through an output filter. It is commonly called as an LC filter, which refine and smoothen the output voltage by mitigate the high frequency component. And last but not least, this regulate voltage is directed into the load to ensure the stable power supply. To mathematically articulate the system behavior, we as engineers derive a transfer function. This function integrates the relationship between the input and output, basically, to enable the precise precision of the converter's response to try to verifying input or load condition. The transfer function and of analysis in comprehending and fine-tuning the buck converter performance for diverse applications in power electronics. So moving on to the next question. In this part, I need to explain this is how so in this part, I need to find the transfer function. In order to get the transfer function, I assume RC is equal to 0.9, and we get the value of gain Vin over LC, and we get the value of gain is 5.1369, and after that we find the value of transfer function by using the ESR filter, as you can see in the slide, in this formula. Then we insert all the value from the previous calculation, and we get the transfer function is 3.5154 milli and so on, as you can see here. And then I need to find the value of Kp, the two value of Kp, 0.16673 and 0.0169. And after that, we were assigned to design a switch mode power supply. We were given a value of DC V output, AC V in to 240 VRMS and 50 Hz. And we will assign it to choose the value of voltage ripple, and we chose 0.02, and the ratio we stated 5 and 1, and the value of switching frequency is 50 kHz. After that, we need to find the parameters for all these design and switch mode and supply. As you can see here, I calculate the value of duty ratio, inductor minimum and maximum, the value of capacitor by using the R formula, and also I need to find the inductor maximum and minimum, and also this one. All the all the value calculated, you can refer into my slide, which is as you can see in this screen.
Now I'll explain about the simulation part. So this is our feedback controller for buck converter. As you can see here, first on the left is the PID controller. In this PID, we will put the KP and KI old and new based on our calculation. And after that, there is a saturation, then PWM, and after that is a buck converter. So in this buck converter, we will put our inductance, capacitance and resistance based on our calculation, which is for inductance is 0.3383 millihenry, and the resistance is 6.5 ohm, and for capacitance is 3.906 microfarad. So lastly, this the scope. So based on this result on board diagram, you can see here that when we put the KP old 0.5 and KI old 5000, the frequency we get is 267 Hz and the phase margin is 92.7. After that, when we adjust the KP, when we calculate the KP new, we get 100 and 103.76, and the KI new is 96.38. So the result in frequency, we got frequency of 33.6 kilohertz and phase margin of 26.9. So this is the comparison before and after. So the frequency crossover, as I said before is 267 hertz, and after new KP and KI 33,600 hertz, and the phase margin is from before 92.7 to 26.9. The gain margin is negative 67.1 dB to negative 30.4 dB. For pole zero map, both have the same, which is left half plane, and for the stability part is based on our calculation and also simulation. We got that the KP new and KI new result is more stable. Next is our buck converter with feedback converter. So this diagram is our design, our circuit design. In this diagram, there is resistance, inductance, and also capacitance. So this parameter, we put our own calculation. We put the calculation result value. Next, this is our carrier signal waveform, which is supposedly to look like a sawtooth waveform. So we got the sawtooth waveform. So next is gate signal waveform. Based on this gate signal waveform, we can calculate the duty ratio. So this is maximum and minimum inductor current. As you can see here, the upper peak is the maximum inductor current, which is about 5.38, and the lower peak is the minimum inductor current, which is about 4.7 ampere. Next, this is our voltage output waveform. Based on this voltage output waveform, we can calculate the voltage ripple. So this is the comparison between our simulation and also calculation. For the duty ratio, based on calculation, we got 0.4714, but in simulation, we got 0.3821. The percentage error is 18.9%, which is quite high. So next is minimum inductor current, which is IL min. For the calculation part, we got 4.5 ampere, and the simulation is 4.40 ampere. The percentage error for this is 2.22%. And maximum inductor current IL max, based on calculation, we got 5.5 ampere, and the simulation is 5.38 ampere, the percentage error is 2.18%. For the ripple inductor current, based on calculation, we got 0.5, and for the simulation is 0.49. And the percentage error for this is 2% only. So the average inductor current is based on calculation is 5 ampere, and for simulation is 4.89 ampere. The percentage error is 2.2%. The output voltage for calculation is 32 volt, and the simulation is 33.42 volt, and the percentage error is 4.25%. For the peak-to-peak ripple voltage, the calculation is 0.64 and the simulation is 0.67. So the percentage error is quite high, which is 4.48%. And lastly, for the ripple factor, based on calculation, we got 2% and the simulation is 1.97, which is good because below than 3% based on the question. So the percentage error for this is 1.5%. So that's all from us. Thank you very much.